Ma'am, good evening, ma'am.
Good evening, sir. You can start now, sir.
Yeah, yesterday we were learning about the extraction of iron from hematite ore. And we will continue with that extraction of iron, and then we'll go from copper, Ehlingham's diagram. Possibly we will.
Good evening, sir.
Yeah. Then
Good
Lakshmi. Good evening, then Lakshmi. Yeah. Extraction of iron. We'll learn the flow chart for the extraction of iron from hematite, and then we'll continue with the next part of the topic. Now, yesterday I was discussing something with respect to charge. What is charge? Charge is ore plus coke and limestone in the ratio 8:4:1. This is called as charge. So charge is, now we'll learn the flow chart so that you understand. Iron ore is concentrated. First, it's concentrated by gravity-based separation. You know what is gravity-based separation. So it is based on density, gravity-based separation or leviation. So the first step is the iron ore is concentrated by gravity-based separation. Then it is calcined. Calcination. Calcination is heating in the absence of air or minimum supply of air to drive away moisture, to expel the volatile impurities. We calcine. Once calcination is done, charge is introduced into the furnace. Charge is introduced in the furnace. When charge is introduced in the furnace and heated, now we have coke also. Coke is there, and oxygen is passed through the tires, and we heat it. When we heat it, what happens is the first step I told you, it is called as zone of combustion. Zone of combustion. So combustion, this carbon burns with oxygen to form carbon dioxide, giving enormous amount of energy. That's around 1600 degrees Celsius. The temperature will increase to 1600 degrees Celsius. The carbon dioxide gas formed will move to the cooler region. The second step is called as zone of fusion, or it is also called as absorption, zone of absorption. So this carbon dioxide will react with unreacted coke to form carbon monoxide. It is an endothermic reaction. Here heat is absorbed. Therefore, temperature from 1600 decreases to 1300 degrees Celsius. Now, we have also learned the third step, that is zone of slag formation. Zone of slag formation. The zone of slag formation, this limestone will decompose to form calcium oxide, giving you carbon dioxide. This calcium oxide, which is formed, will react with the impurity. The impurity is sand here. This is a gangue particle. This is the flux. So therefore, you get calcium silicate. Now they can ask you for 1 mark. What is the slag formed in the extraction of iron? The slag formed in the extraction of iron is calcium silicate. Now, next, the fourth step is reduction or smelting, maybe. We can call it a smelting. So what happens is this hematite Fe2O3 will be reduced by carbon monoxide to form iron and carbon dioxide. Now, here in the furnace, we can say carbon monoxide reduces iron, hematite, to iron. This is a reaction I've written here. Now, once it has been reduced maybe I should write it like this. It is not, okay, like this, So once it has been reduced, what we get is we get a spongy iron. The spongy iron, or it is also called as cast iron. This is also called as not pig iron, it's also called as pig iron. This is also called as pig iron. Now, this pig iron contains around 4% carbon. Now, when you heat it with scraps of iron and coke, we get wrought iron. Iron and coke, we get cast iron, CAST, cast iron. This cast iron contains around 3% carbon. Here it is 4% carbon. Pig iron contains 4% carbon. This cast iron will contain 3% carbon. This, when you heat it in the reverberatory furnace, you get wrought iron. This wrought iron is the purest form of iron. It contains around 2.2 to 2.5% carbon. This is what we learned. This is a flow chart. They can ask you sometime the flow chart of extraction of iron. They can ask you to draw the diagram and write the reactions. 5 reactions you are supposed to write. Did you follow this?
Yes, sir.
Now, what is the reducing agent in the extraction of iron? Coke and a carbon monoxide is a reducing agent. What is the function of coke? Carbon. The function of coke or carbon acts as a fuel. It gives you energy for the reduction of iron. It gives heat. So therefore, coke acts as a fuel. Next, what we have is copper. We'll have to learn something called as Ellingham's diagram. I will teach you Ellingham's diagram after learning copper aluminium extraction. All right. Now, copper extraction is done using copper pyrites. Maybe I'll check whether there's any place. Yeah. I will teach you the copper extraction. The next one is extraction of copper. Extraction of copper. Extraction of copper from copper pyrites. The ore used for extracting copper is copper pyrites. So the formula of copper pyrites is CuFeS2. The molecular formula of copper pyrite is CuFeS2. Now, what is the first step in the extraction of any metal? The first step in the extraction of any metal is the pulverization process, that finally powdering, that is a common process. Once that is done, then the next step involved is concentration. I clearly explained what is concentration. Concentration is nothing but increasing the percentage of the metal in the ore is called as concentration. Now, sulfide ores are always concentrated by froth flotation. You should remember. So froth flotation, you should write the iron pyrites or the copper ore is concentrated by froth flotation. Once concentration is done, the second step, sulfide ore are always roasted. Roasting is heating the concentrated ore in the presence of sulfur. When you roast copper pyrites, what will happen? Roast is heating, the presence of oxygen is called as roasting. So copper pyrite is CuFeS2. When you heat it in the presence of oxygen, it gets reduced to copper sulfide, iron sulfide, and gives sulfur dioxide gas. So this copper pyrites gets converted to cuprous sulfide, iron sulfide, liberating sulfur dioxide gas. Now, these sulfide ores, now when I say these sulfide ores, that is copper sulfide and ferrous sulfide, are oxidized in a blast furnace. Now, blast furnace, I told you it is a vertical furnace. Right here also, we are using a blast furnace. So what happens in blast furnace? Now, this copper sulfide, you take copper sulfide and ferrous sulfide mixture in the blast furnace and heat it in the presence of air. You heat it. So what happens is this copper sulfide, CuS2, will get oxidized to cuprous oxide, giving you sulfur dioxide. So that means sulfur gets eliminated as sulfur dioxide. So copper gets oxidized to copper oxide. Likewise, if you have iron sulfide, this iron sulfide, iron sulfide is there. That also gets oxidized to iron oxide, liberating sulfur dioxide gas. So sulfur dioxide gas gets liberated. Most of the sulfur dioxide gas gets liberated. So this is the first step in the extraction of copper by copper pyrite. So what are the first step? The first step is concentration. It's concentrated by froth flotation. It is roasted so that copper pyrites gets converted to copper sulfide and iron sulfide. These sulfides of copper and iron is taken in the blast furnace and heated in the presence of oxygen or air. So copper sulfide gets converted to copper oxide. Ferrous sulfide gets converted to ferrous oxide. Now the third step here is smelting. The third step is smelting. The smelting, we know that it's heating in the presence of a flux. So the mixture is what is smelting here done? The mixture contains roasted ore. Mixture contains roasted ore plus coke plus sand. Here, sand acts as a flux. Here, sand acts as a flux. In the extraction of copper, sand acts as a flux. It is heated in a blast furnace. When we heat in a blast furnace, it's heated in a blast furnace. So what happens when you heat in the blast furnace? Now, in the previous equations, see a lot of equations we have to learn here. Now, you have ferrous sulfide as well as you'll have copper sulfide. Now, what happens is the following changes takes place. The first one is iron sulfide. Iron sulfide, FeS, gets oxidized because you're heating it in the presence of air. It gets oxidized to ferrous oxide, liberating sulfur dioxide gas. This ferrous oxide, which is formed, will react with sand. Sand is a flux. This is an impurity. It's a gang particle. It is a flux. Gives you FeSiO3, iron silicate. This is a slag, iron silicate. A slag will be formed. This is the first step in smelting. Now, cuprous oxide is also there. This cuprous sulfide will be oxidized, 2 moles of cuprous sulfide. 2 moles of cuprous sulfide will be oxidized to cuprous oxide, giving you sulfur dioxide gas. This cuprous oxide, which is formed, will react with iron sulfide to give cuprous sulfide plus iron oxide. Now you can see here, you have cuprous oxide and cuprous sulfide. This cuprous oxide and cuprous sulfide together, or maybe not together, this cuprous sulfide with the traces of unchanged ferrous sulfide is called as copper matte. They can ask you for 1 mark. What is copper matte? Objective type. So it's a mixture of cuprous sulfide and traces of ferrous sulfide. Traces means small amount. FeS, traces of ferrous sulfide is called as copper matte. Are you following? There's so many reactions we are learning. Are you following? Yeah? Are you there? All right. Now, once you have done with the fourth step here, what you're supposed to learn, the last step is called as bessemerization. So they will not ask you the whole thing for 3 mark, right? They can ask you bessemerization for 3 mark. They can ask you what is copper matte for 1 mark, right? Now, this bessemerization, you have a pear-shaped container, and which is connected to a stand like this, and you have a provision to pass hot air. We can pass hot air into it, and we have minute pores here. It's called as tuyers. These are called as tuyers, wherein TUYERS ERES, wherein you can pass oxygen gas. Right? Now, copper matte is taken into it. What is taken into it? Copper matte along with sand. And you heat it. So when we heat it in the Bessemer's converter, what happens is, the iron sulfide present will get oxidized to iron oxide, liberating sulfur dioxide gas. This iron oxide, which is formed, will react with silica, that is sand, to give iron silicate a slag. Likewise, we have cuprous sulfide. This cuprous sulfide reacts with oxygen to form cuprous oxide, giving you sulfur dioxide gas. This cuprous sulfide will react with cuprous oxide. So not all the cuprous sulfide will be oxidized to cuprous oxide. Traces of cuprous sulfide will be left out. That will react with cuprous oxide to give copper, liberating sulfur dioxide gas. Now, since the sulfur dioxide gas is liberated, there will be bubbles formed on copper. Therefore, this copper is called as blister copper. Now, you can see this is an example for auto reduction. It's an example for auto reduction. So auto reduction, or it's also called as self-reduction. What is this auto reduction or self-reduction? A process in which one of the product itself behaves like a reducing agent is called as auto reduction or self-reduction. So here copper sulfide will reduce copper oxide to copper. So copper sulfide form itself will behave like a reducing agent, and the copper, blister copper, which is obtained, is around 98%. It's around 98%. All right. Now, are you there? Are you able to follow something?
Yes, sir.
Yeah. See, this reaction you have to concentrate. I will teach you this reaction. So many reactions we have learned, but I will teach you it in a simpler way possible. This is a long question which cannot be asked for 3 marks, the whole thing. Now, I need some space, so I will teach you. Let me see, is there any space? Yeah, this will be okay. Now, we'll learn the flow chart of extraction of copper. Flow chart. So this flow chart, if you remember, you should be in a position to write this. Now, the first one is copper pyrite. The ore is copper pyrites. Copper pyrites is CuFeS2. What is copper pyrites? CuFeS2. This copper pyrite is crushed. CRUSHED, crushed to small pieces. Once it is crushed, then it is subjected to concentration. What is the method of concentration? It is froth flotation. Because it's a sulfide ore, it is froth flotation. Once froth flotation is done, then it is subjected to roasting in the reverberatory furnace. Roasting in the reverberatory furnace. So when you roast, what happens? This copper pyrites, CuFeS2, when you roast, the presence of oxygen, this will get converted to cuprous sulfide, iron sulfide, FeS, and you get sulfur dioxide gas. So sulfur dioxide gas gets eliminated. So you'll get cuprous sulfide and ferrous sulfide. Now, after roasting, this is taken in blast furnace. A blast furnace is a vertical furnace, and it is heated in the presence of ore, coke, and silica. That is sand. Silica is sand. It's a flux, remember. So what happens when you heat it in the blast furnace? The iron sulfide, FeS, iron sulfide, will get oxidized to iron oxide, giving you sulfur dioxide. And likewise, this iron oxide which is formed will react with sand. Sand is silicon dioxide, to give iron silicate. It gets eliminated as a slag. Now, once it gets eliminated as slag, what happens is you will have this copper sulfide and traces of FeS. Not all FeS will get converted. So this traces of copper sulfide and FeS together is called as copper matte. It's called as copper matte. I hope that you understood till here. The first one is copper pyrite, CuFeS2. It is crushed to a small piece, crushed, CRUSHED, crushed. And then it's subjected to froth flotation. Once froth flotation is done, that is concentration. Concentration is done by froth flotation. Once concentration is done by froth flotation, then it is subjected to roasting. What is roasting? Roasting is heating the concentrated ore in the presence of oxygen. When you roast copper pyrites, this copper pyrites gets converted to copper sulfide and iron sulfide. Now this sulfur dioxide gets eliminated. Now this copper sulfide and iron sulfide, along with that you take coke and silica in the blast furnace. When you heat it in the presence of oxygen, iron sulfide gets converted to iron oxide. This iron oxide gets reacting with sand to form, or silica to form calcium silicate. It's a slag. Not all. So traces of FeS will be there along with this copper sulfide. So that's called as copper matte. That's called as copper matte. Now, this copper matte is taken in a Bessemerization, Bessemer converter, or Bessemerization is done in Bessemer converter in the presence of air. So what happens? Now, copper matte contain iron sulfide. This iron sulfide reacts with, heated with the presence of oxygen, you get iron oxide liberating sulfur dioxide. This iron oxide which is formed, the traces of iron sulfide which is present in the copper matte will get converted to iron oxide liberating sulfur dioxide. This iron oxide will react with sand to form iron silicate slag. Now, this copper sulfide and copper oxide which is formed will get auto conversion or auto reduction to form copper with liberation of sulfur dioxide. This is called as blister copper, BLISTR copper, blister copper, which is 98% pure. Did you follow this?
Yes, sir.
Now we will have to learn another two extraction. The other two extraction are very simple. We will learn the other two extraction and then we will continue with the topic of the chapter. Now, the next one is extraction of zinc. Extraction of zinc from zinc blend. The zinc blend is ZnS. Zinc sulfide is called as zinc blend. Now, since it is a sulfide ore, the first step is concentration. It is concentrated by froth flotation. Concentrated by froth flotation. The second one is roasting. So roasting, once you concentrate, the zinc sulfide is heated in the presence of oxygen So what happens? The zinc sulfide gets oxidized to zinc oxide, giving you sulfur dioxide, or zinc sulfide gets converted to zinc oxide, giving you sulfur dioxide gas. 2 moles of sulfur dioxide, balance the equation. So it will be 3 here, 3 moles of oxygen. So zinc oxide. The third step is reduction. This is very simple, reduction. Now the zinc oxide which is obtained is heated with coke at 1673 Kelvin. When you heat it with coke, coke is a reducing agent here. What happens? Carbon and oxygen gets eliminated as carbon monoxide and you get zinc. Zinc. This metal is distilled off and collected by rapid cooling. So both will be in gaseous state. Both will be in gaseous state. You have to rapidly cool. When you rapidly cool, what happens is zinc gets distilled. Zinc gets distilled. It means zinc solidifies. Carbon monoxide does not solidify. It gets eliminated. So this is how you prepare the zinc extraction. So 3 steps. It's a very simple reaction. Only 2 reactions you're supposed to know, right? So zinc blend on roasting gives zinc oxide, liberating sulfur dioxide gas. And the zinc oxide is reduced using carbon at 1673 Kelvin. You get zinc and copper together. The zinc and copper together is called as zinc spelter. Zinc spelter, Z-I-N-C S-P-E-L-T-E-R, zinc spelter. So on rapid cooling, zinc gets distilled so that we get zinc. Now, next, what we have is extraction of aluminum. See, zinc extraction, they have not asked for a long time. They are asking for iron extraction. They're asking for chemical method of concentration of aluminum ore, bauxite, Bayer's process. And they're also asking extraction of aluminum by from bauxite, Hall-Hérold's process. We need to learn Hall-Hérold's process. Now, the next what we have is extraction of aluminum. So aluminum is purified by a bauxite ore is purified by Bayer's process. Bayer's process is a chemical method. I have taught you Bayer's process. Now, extraction of aluminum from bauxite. This process is called as Hall-Hérold's process. H-E-R-O-U-L-T-S. Hall-Hérold's process. Now, in Hall-Hérold's process, what's that we do is, let me see whether there's a picture anywhere represented for aluminum. Just give me some time. Aluminum. No. All right. So we will learn. Hall-Hérold's process. Now, in order to understand the extraction of aluminum, it is by electrometallurgy. It's an electrometallurgical process. That means we need to have a current. We need to have current. So in order to prepare a cell, so they take an iron tank. We take an iron tank. Sorry. We take iron tank. Inside the iron tank, we have, this is iron tank. Maybe I'll try to draw neatly. This is iron tank. Inside this iron tank, we have a carbon lining. We have a carbon lining like this. This is iron tank. Iron tank. This is carbon lining. Carbon lining. And we have graphite rods. We have graphite rods. These graphite rods are connected through a clamp which is connected to the positive terminal. Connected to the positive terminal. So this graphite rods acts as anode. This graphite rod acts as anode. And this carbon lining acts as cathode. Cathode is a negative electrode, remember. Cathode is a negative electrode. And inside this, we take molten electrolyte. Molten electrolyte, semi-liquid electrolyte, molten electrolyte. And at the top of this, we place, at the top of this, at the top of this, 1 minute. at the top of, where is that? At the top of this, we have powdered carbon. This is powdered carbon. Powdered carbon. Now, not only we have molten electrolyte, along with molten electrolyte, we will be taking some more mixtures. I will tell you what's that. So aluminum is obtained by electrolysis of pure alumina, that is from bauxite, right? This molten electrolyte contains bauxite. It contains cryolite. The cryolite is sodium aluminum fluoride is cryolite. Along with this, you have something called as fluorospar. This fluorospar is nothing but calcium fluoride. So this molten electrolyte contains bauxite ore, cryolite, and fluorospar. Now, what is this? Pure bauxite, pure alumina is a non-conductor. Pure alumina is a non-conductor. So to improve the conductivity, we use cryolite. To improve the conductivity of pure alumina or bauxite, we use cryolite. And small amount of fluorospar is added to bring down the fusion temperature. Now, when I say bring down the fusion temperature, it means to bring down the melting point of alumina. So these are the functions of cryolite and fluorospar. So I hope you're following what I'm trying to write and explain. Yes?
Yes, sir.
Now, see, in the Hall-Herold's process, you will take iron tank lined inside by carbon, which behaves like cathode. Graphite rods will be immersed, thick graphite rods that will be connected to the positive terminal. It acts as anode. Inside the cell, we will take molten electrolyte. This molten electrolyte will contain alumina. Alumina is Al2O3. Alumina, cryolite, and fluorospar. This pure alumina is a non-conductor. So therefore, to improve the conductivity, we will use cryolite. Cryolite is sodium aluminum fluoride, NaAlF6. This is sodium aluminum. Was it Na3? Sorry, there's Na3 because valency is not balanced. Valency is not balanced.
Sir, it's not visible, sir.
It's not visible. Oh
No,
my
sir.
God! Again. Now it's visible.
Yes, sir.
So this is Na3Al(F6), sodium aluminum fluoride. That's cryolite, which increases the conductivity. So now what happens is, on passing current? What happens is electrolysis will take place. When we say electrolysis will take place on passing current, electrolysis will take place. So what happens? This alumina, in the presence of carbon powder, will dissociate to form aluminium, liberating carbon dioxide gas. This is the overall reaction. But what happens? The stepwise reaction at anode. At anode, what happens? This Al3 plus, this is an anode. What happens? Anode is graphite. Graphite is made of carbon. Oxygen moves, right, to form carbon monoxide. It's a gas giving it 2 electrons. And this carbon again reacts with maybe more of oxide ions to form carbon dioxide, giving you 4 electrons. At anode, carbon dioxide gas is liberated. Now at cathode, what happens? Cathode is a negative electrode. Aluminum ions move towards cathode. These aluminum ions will accept 3 electrons and gets reduced to form Al. So this is the reaction which takes place in Hall-Herold's process. Now this At cathode, aluminum is reduced. Aluminum ion is reduced to aluminum. So this is Hall-Herold's process. Just go through this Hall-Herold's process. Then we will continue with the last part of the topic. No, not last part of the topic. We have some more things to be learned. We have to teach you hydrometallurgy, and then I have to teach you Ellingham's diagram. Ellingham's diagram in a few minutes we'll finish. Today we'll finish the topic, and then we'll go for the class questions, CET questions or MCQs, sorry, in the next class. Followed with this?
Yes, sir.
Yeah. Coming to the hydrometallurgy. What is this hydrometallurgy? Hydrometallurgy, I told you, it is used for extraction of pure noble metals. Hydrometallurgy. Now, there was a long time, there was information in the news channels. That is, the people used to come in the home, come to our home and ask people, we will wash gold and give you. We will clean gold and give you for lesser cost. So all the women, most of the women used to, it happened in Karnataka. So most of the women used to give the gold. What happens that time? When people give gold, so what happened at that time is the gold was dissolved in cyanide solution. So people used to bring sodium cyanide solution. So gold is not soluble in any of the acid. Gold is a noble metal, it does not react. But gold is soluble in sodium cyanide solution, aqueous, in the presence of oxygen. So you should remember this ratio, 4:8:2:1. This is 2 moles of water, 2:1. So what happens that time? Since gold dissolves in sodium cyanide, what happens? A layer of gold will dissolve. Then you remove the gold from the solution, what happened? It looks very shiny. So people thought gold is clean, but actually what happened? Some amount of gold was dissolved in sodium cyanide. So people took gold and went. This was a major news in Karnataka once upon a time. So this ratio you should remember. Gold is soluble in sodium cyanide. It's done in wooden vats, wooden containers, right? So when it dissolves in sodium cyanide, we get a complex called as complex like this, 4 moles of NaAuCN twice. Plus, you get sodium hydroxide. You get sodium hydroxide. It is a complex. You can name this IUPAC. Sodium dicyanidoorate, oxidation number you write. It should be +2 or something. You can write. Now, the second step here is the sodium orocyanide, which is formed. Sodium orocyanide, I'll write it like this. Sodium, 2 moles of sodium orocyanide, AuCN twice, is allowed to react with less electropositive metal like zinc. When less electropositive, it means more reactive. Standard, not less electrode potential. So zinc is more reactive than gold. So therefore, what happens? Zinc will displace gold. When zinc displaces gold, what's that we get? You get Na2ZnCN4. Plus, you will get gold. So this is a pure form of gold. So extracting a metal in solution state is called as hydrometallurgy. So what is that? How will you write the statement? A noble metal like gold and silver are extracted by hydrometallurgy. Gold and silver is dissolved in sodium cyanide solution in the presence of oxygen to form a corresponding cyanides. This corresponding cyanides is allowed to react with a more reactive metal like zinc. Therefore, we get a pure gold. Now you can write this. The same reaction you can write in place of Au, you can use Ag. It becomes silver. So you will get the silver complex, and also silver complex can be reduced to silver by using a more reactive metal called as zinc. Followed So extracting
Yes,
noble
sir.
metal, extracting metal in the solution state. This also can be asked for true marker reactions. Important. Now coming to the last part of the topic, is called as Ellingham's diagram. We will learn Ellingham's diagram. Give me some time, I'll erase this. Practical got over for you?
Sir, tomorrow we are having, sir.
What practical tomorrow?
Tomorrow physics, sir. Day after tomorrow chemistry, sir.
Prepared, huh?
Yes, sir.
Hmm.
Preparing, sir.
Preparing. No problem. It will be easy. Don't worry.
Yes, sir.
Yeah. Now, the last part of the topic is called as Ellingham diagram. I should have done this along with the extraction of iron, but anyways, I thought this is a little complex, so I thought we will learn Ellingham's diagram at the end. But it's actually very interesting, and it's, but they'll ask you only the definition of Ellingham's diagram, or they can ask you based on Ellingham diagram, iron also. We will tell you. Ellingham. Ellingham is the name of a scientist. Ellingham's diagram. All right. Now, what is this Ellingham's diagram? Now, firstly, we should understand why we have to learn Ellingham's diagram and what is Ellingham's diagram. The definition of Ellingham's diagram is it's a graph of standard free energy change as a function of temperature. So Ellingham's diagram is a graph of standard free energy change as a function of temperature. I will draw the graph and explain later. Now, what's the purpose of using Ellingham's diagram? Now, before we learn the purpose of Ellingham's diagram, graph of standard free energy change as a function of temperature for the formation of oxides, chlorides, or sulfides is called as Ellingham's diagram. What is Ellingham's diagram? It's a graphical representation of standard free energy change as a function of temperature for the formation of oxides, chlorides, and sulfides. Now, why we have to learn Ellingham's diagram? Ellingham's diagram we learn to choose suitable reducing agent. To choose suitable reducing agent, we need to learn Ellingham's diagram. Not only to choose the reducing agent, and also the optimum temperature for reduction. Optimum temperature for reduction. These are the functions of Ellingham's diagram. What are the functions of Ellingham's diagram? One is to choose the reducing agent, suitable reducing agent. The second one is to choose the optimum temperature. Optimum temperature means the temperature at which the reducing agent is highly active. That's called as optimum temperature. Now, I will draw a very few graphs only. This is standard free energy change as a function of temperature. You can refer your notes. I don't have the picture right now. Right. So we will plot a graph. This is 0. This is minus 200. This is minus 400. This is minus 600. This is minus 800. This is minus 1000. And this is minus 1200. Maybe we'll write this as minus 1200. Now here, this is 0 degrees. This is 400 degrees Celsius, 800 degrees Celsius, 1200 degrees Celsius, 1600 degrees Celsius, 1600 degrees Celsius. Now, what happens is few graphs we will learn. One is this. I write this, it looks complex. 4 by 3 Al2 Al. All right. plus O2, giving you Al2O3. Next, I will write, maybe around here, I will write for chromium plus 3/2O2, giving you Cr2O3, chromium. I will write here 200. I will draw this graph. This is HGO formation. And I will write this graph like this. This is for Ag2O, silver oxide, Ag2, silver oxide, Ag2. I've drawn only 4 graphs. Now, carbon cannot be used as a reducing agent for all. Now, before we learn the properties, first we learn the salient features of Ellingham's diagram. Now, you can see this is minus 100, this is plus 200. So, as you see, now minus 800 is greater than minus 1000. Yes or no? Minus 800 is greater than minus 1000. So, as temperature increases, what's happening? The free energy also increases. As temperature increases, free energy also increases. So therefore, the graph shows upward deviation. Are you following? You can see the graph shows upward deviation. So as temperature increases, free energy also increases. That's the first point. As temperature increases, delta G naught also increases. Second point, at phase transition, there is a drastic change in entropy. Therefore, there's a drastic change in delta G naught. You can see phase transition. What do you mean by phase transition? Solid to liquid or liquid to gas or any other change, physical change takes place. That's called as phase transition. So as phase transition, there's a drastic increase in free energy. You can see this is the point. This is phase transition, drastic increase. All right. Second point. That's the second point. Third point, metal oxide, which is below, is more stable than metal oxide above. Meaning, aluminum oxide is more stable than chromium oxide. That is what the statement. So I've written only 2 for our example. You would have seen the Ellingham diagram. It's just a highly complex graphs. So metal oxide, which is placed below, is more stable than the metal oxide, which is placed above. The fourth point, metal placed below can reduce metal oxide placed above. These are the characteristics or salient features of Ellingham's diagram. All right. The fifth point is when delta G becomes positive. When delta G becomes positive, it undergoes thermal decomposition. These are the 5 points in case of Ellingham's diagram. The first point is, as temperature increases, standard free energy increases. Therefore, slopes shows positive deviation. The next one is, at phase transition, there's a drastic increase in standard free energy change. The third point, the metal oxide which is placed below is more stable than the metal oxide which is placed above. The metal which is placed below can reduce the metal oxide which is placed above. And the fifth point is, when delta G becomes positive, it undergoes thermal decomposition, no reducing agent required. So these are the characteristics of Ellingham's diagram. Did you follow this?
Yes, sir.
Now, we also learned something called as aluminothermite process, if you remember. Aluminothermite process. Now, what is this aluminothermite process? Reduction using aluminium will be called as aluminothermite process. Now, chromium oxide, when you heat it with aluminium as a reducing agent, we get aluminium oxide giving you chromium. So this is a reduction process. You can see this is chromium oxide, this is aluminum oxide. Aluminum oxide is below chromium oxide. That means aluminum oxide is more stable compared to chromium oxide. Therefore, when chromium oxide is heated with aluminum, what happens? Aluminum will react with oxygen to form aluminum oxide, which is more stable, giving you chromium. That is what I told you. Now, any metal which is placed below, can reduce the metal oxide which is placed above. Now, for an example, if I have magnesium here, magnesium can be used as a reducing agent. But what happens is magnesium boils away, becomes vapor at 800 degrees or 1000 degrees Celsius. Therefore, magnesium cannot be used. But did you follow what I'm telling? The transition temperature of magnesium is low. Therefore, magnesium cannot be used. So any metal which is placed below can be used as a reducing agent for the reduction of the metal oxide which is placed above. We have to learn in more specific Ellingham diagram with respect to iron, copper, and zinc. We will learn that in the next class. But I hope you understood what is the definition of Ellingham's diagram. It's a graphical representation of standard free energy change as a function of temperature for the formation of oxides, chlorides, or sulfides. Did you follow this? Why you have to learn Ellingham diagram? In order to learn or find suitable reducing agent, and also to find what the optimum temperature. I've taught you about the salient features of Ellingham's diagram also. So you can just go to the salient features of Ellingham's diagram. If you have any clarification, you can ask. I have to continue with Ellingham's diagram of iron, copper, and zinc. It will not be able to finish it today. So in the next class, maybe on Friday, we'll finish off with this chapter. We'll learn some of the MCQs as well as this Ellingham's diagram concept. All right. Anything else? If you have doubts, you can ask me.
No, sir.
No? All right. Ma'am? Ma'am, I'll stop the class, ma'am.